Professor Tshilidzi Marwala. He is, by title, the Vice Chancellor at UJ, University of Johannesburg. And amongst all his qualifications, I think a few things that are quite cool about him is that he has obtained his PhD in AI and engineering from the University of Cambridge, which explains why he was so excited that all the presidents were engineers. And besides the fact that he's sporting very cool blue Jordans today, he also has published 12 books in artificial intelligence. He has over 300 journal publications in AI, and today he'll be speaking on the rationality of artificial intelligence machines. Let's welcome him.
Sanibonani. Sanibonani. Thank you very much for inviting me to come. This is actually my first time coming to the Deep Learning Indaba. Benjamin. But I don't feel completely like a stranger because two of the eight founders were both my master's students. You know, I did introduce them to Shakir Muhammad and Fukosi Maribate, where I introduced them to artificial intelligence. Now, what I really want to talk about this morning is on rationality of machines. Can machines be rational? How many of you know what rationality is? Please raise your hands. Okay? By the time you finish this talk, you will all know what rationality is. May I take out my jacket, please? So one of the things that I miss the most, being a vice chancellor, is actually to teach. I think teaching is, Dr. Makondo, teaching is a calling, not a job. So now, this talk, I really will start. It will cover some of these issues. What is rationality? It will also cover my theory called flexibly bounded rationality. Obviously, bounded rationality is a big theory that Herbert Simon was actually a political scientist. He studied political science. And he is the only person to win both the Turing Award and the Nobel Prize. He was one of the fathers of artificial intelligence. There used to be an AI program called Lisp. The S is Simon, after him. And then I will talk about rational choice, rational opportunity cost. Can a machine be rational? Can we measure rationality? And is machine rationality subjective? Group versus individual rationality. And I will end with rational markets. But before I talk about rationality, I really wanted to talk about this issue called the Fourth Industrial Revolution. A few years back, I had dinner with Shakir Muhammad. And he told me that, everybody is talking about the Fourth Industrial Revolution. But we who work for Google, here at Google, nobody talks about it. Why is it that, those who are talking about it are doing very little, and we who are doing everything are talking less about it? But I think sometimes ideas are quite important. Now, what is this thing called the Fourth Industrial Revolution? For us to understand the Fourth Industrial Revolution, we should understand the Industrial Revolution, the history of the Industrial Revolution. We all know that the first Industrial Revolution happened in England. It's amazing, isn't it? I was a PhD student there, I was a postdoctoral student there. And if you just wander around to a pub and you interact with people, you would wonder how in the world did such people came up with the Industrial Revolution. But it happened in England, and from a probabilistic perspective, it was supposed to either happen in China or India. And the reason why it happened in England was because of the scientific revolution that preceded it. We all know about Newton's laws of motion. We all know about Newton's incomplete conception of gravitation. He invented gravitation, or he discovered it. We all know about Newton's law of cooling. All those scientific revolution were quite instrumental in the first industrial revolution. And what happened was that steam engine was discovered, trains were discovered, and quite a great deal of producing goods and services was for the first time done by machines. When this came about, not everybody was happy. There were people who were saying that these machines are actually taking away our jobs. And these people are called the Luddites, Luddites. And many of them actually were hanged, because what they would do, they will organize themselves and they will go to companies and they will try to destroy the machines. And many of them were arrested. The Luddites died and the Industrial Revolution marched on. So we cannot stop the progress of technology. The second industrial revolution actually happened as a result of scientific developments in England, mainly in Europe. So Hans Christian Ørsted actually observed that when you have something that conducts electricity, if it is conducting electricity, then there is a magnetic field around it. You still remember the right-hand rule? Still remember it? That if the current is going this way, the magnetic field is going this way, isn't it? Now, that was a powerful invention. And obviously, it took Faraday to say, how about if I put a permanent magnet next to a magnet that is generated by the movement of electricity? What will happen? And of course, we know what happens. If you have electricity flowing, the conductor will move. And this is the birth of the electric motor. And the electric motor is one of the biggest unsung heroes. It revolutionized the assembly line, mass production of goods and services. It revolutionized refrigeration. We tend to forget that when Queen Victoria wanted her ice cream, she used to import ice blocks from the North Pole. And of course, when you have an electric motor now, you can be able to have an effective compressor, which is what you need in order to do refrigeration. But the corollary of that, if you have something that conducts electricity, and you put it next to a magnet, and you move it, what happens? Electricity is generated. You are looking at me like I'm speaking about witchcraft. It's not witchcraft, it's science. Now, even up to today, almost more than 90% of electricity that is generated today is generated by moving a huge conductor located next to a magnet. So Eskom takes coal, heat water, steam comes out, it moves a conductor that is standing next to a magnet. For nuclear technology, the same process. Nuclear radioactive material are heavy material that are not stable unless they emit energy, and that energy that is emitted obviously is used to heat the water that ultimately actually moves the conductor next to a magnet. And by the way, the reason why we are having so much problems with Eskom is because they built these two new power stations, Kusile. And those two new power stations, what people don't know is that the heating of water is supposed to produce superfluid, not steam. That's why it is called critical power station. In fact, there is no critical power station that uses superfluid of the scale of the ones that we have built, that has ever been built elsewhere. So that is why you have so many engineering problems. Of course, the second industrial revolution gave us electricity and magnetism. But that's not the only thing that that beautiful theory gave us. Maxwell was not a very educated person, did not go to university. So Maxwell decided to write beautiful equations out of this. They are called Maxwell's equations. It's 4 of them. He had messy equations. Heaviside was the one who reduced them to 4 equations. And these equations were not compatible with Newton's laws of motion. And a Dutch physicist called Lorentz actually came up with, we call them Lorentz transformation now, but they were just correction factors that would make electromagnetism be compatible with Newton's laws of motion. And of course, Albert Einstein was the one who gave a physical explanation to that. Almost to the point that Einstein's theory of relativity used to be called Lorentz-Einstein theory of relativity. For those of you who have studied relativity, and I have actually studied it as a subject, I took it for recreational purposes. It's on my transcript. It's on my transcript. There's so much Lorentz transformation, whether it is a time dilation or length elongation, it's always done through Lorentz transformation. So, this electromagnetism gave us relativity. The third industrial revolution also came with developments in the United States, the semiconductor industry, Francisco, where you have material that conducts electricity under certain conditions. By the way, the third industrial revolution was not the birth of digital technology. Digital technology actually existed. In fact, people were communicating with ones and zeros for almost 100 years when digital technology came. There used to be something called a telegram. You don't know what I'm talking about. But I received, the last telegram I received was when I was doing second year in Cleveland, Ohio, USA, and it was very short. It says, Chianeo is dead, stop. Very expensive because they used to count each word, and basically the way it used to work, they used to use switches. Somebody is sitting on the other side, depending on whether the switch is on and off, they will translate it into ones and zeros. And you used to have people in the post office who were trained to look at those ones and zeros and translate them into words. Until 1991, when I received my last telegram. How many of you know what I'm talking about here? You know what a telegram is? Oh, I am in good company then. So, the transistor was just made the switching on and off efficient. That's really what it is all about. In fact, there is a book called Intel Trinity. How many of you have read Intel Trinity? It's basically a book about the formation of a company called Intel. That they went to this place, it used to be a peach farm, now you call it Silicon Valley, to try to industrialize these things. And of course, at that time, people did not even know about clean room, which is what you need in order to handle semiconductors. So they say 6 months after they started trying to produce these transistors, Shockley, who was their leader, won a Nobel Prize. And they said after he won a Nobel Prize, their opinions did not matter. Every time they went with an idea, he will show them the Nobel Prize medal. And obviously they walked away, and ultimately they founded Intel, which is still a dominant player in the transistor market. So that's the third industrial revolution. Francisco, I was corrected. I mentioned at the Science Forum last year that I don't know of any semiconductor company in the continent. And somebody said, no, there is one. We went and checked it, and we couldn't quite find it. So I think it is safe to assume that we do not have any semiconductor company. almost 70 years after the discovery of a transistor. We can't afford to be left behind. Now we're living in an era called the Fourth Industrial Revolution. Now the Fourth Industrial Revolution is really a confluence of technologies around the digital. The digital technology is reaching its end state. We can no longer build transistors that are smaller and smaller and smaller. The process called Moore's Law. Moore's Law actually exists because we were able to make things smaller and smaller and smaller, and we are reaching our limit. So our computational power is no longer doubling every 2 years, as Moore's Law states. And of course, we'll have to start looking at other technologies of communicating. Quantum computing is a big deal. Quantum computing, it means you don't have to rely on two states, ones and zeros, because of the nature of quantum mechanics. The developments in the physical space, new materials. Because if you think about it, when you think of semiconductor, you think the biggest technological problem is actually to make them small. The biggest technological problem is how do you handle the heat that is generated. So it's really about fluid dynamics. And that is why, after using even your phone, it's very hot, isn't it? Despite the fact that it has fans inside. So again, new materials will probably be able to solve that problem. And obviously, for the first time, we are now better able to handle what is happening in our brain. Because what has happened in the past is that even if you had the most wealth, you couldn't buy intelligence. Where I studied at St. John's College at Cambridge, and nearby there is a college called Trinity College. That is where Nando de Freitas was there. And apparently Prince Charles studied there. With all his powers, he couldn't live with his degree because intelligence could not be bought. But in the fourth industrial revolution, gene editing and so on and so forth, for the first time, those with money will be able to cash, as far as intellectual capability is concerned, they will be able to cash out. So now, Fourth Industrial Revolution is basically about rationalizing our decisions. And that is the reason why I am going to talk about rationality. Now, before I go into the topic of rationality, I just need to talk about this issue of artificial intelligence, because it's one of the biggest drivers of the Fourth Industrial Revolution is artificial intelligence. Now, this is my conception of artificial intelligence. You have this big field called artificial intelligence. It's about making machines intelligent. And underneath, you can think of them as tribes. They normally don't agree with one another for one reason or another. So you have soft computing, something like fuzzy logic. One of my students, Shakir, when he went to Cambridge to do his PhD, his supervisor says, "I'm very impressed with your publication, but one thing that I don't really like is that you use the word fuzzy logic. Don't tell anybody that you worked in fuzzy logic." And then computational intelligence, looking at nature. By the way, the concept of group intelligence was invented in South Africa by an Afrikaans poet called Eugene Marais. He wrote a book called Die Ziel van die Mens, which means the soul of the ant. He was looking at the intelligence of the ant, because they are quite intelligent. They build quite complicated structures. And of course, that was the birth of swarm intelligence, which is now used in drones, a population of drones, how they interact with one another. Obviously, it makes sense. The way a school of fish interact would probably be a better way of organizing a population of drones that are working together. Then you have this thing called machine learning. The term machine learning is, because artificial intelligence is making machines intelligent, machine learning is, yeah. So basically it's a statistical view to building intelligent machines. And within machine learning, then you have deep learning, which is basically a sophisticated neural network. It's not a new idea, it's an old idea. When I was doing a PhD, I was working on multi-layer perceptron. And it was not, it was 20 years ago, 22 years ago, but the perceptron was even older than 22 years. So what happens is that we have better computational power to be able to train, because training is very, very important. The estimation of the gradient, of course, this comes from Newton's method, that you can be able to estimate the next solution by combining the current solution with the gradient of that point. You can be able to calculate these things much, much more easier using back propagation, and you can make them complex. So I think the developments of deep learning owe more to computational capabilities than to actually genuinely new innovations. Almost all the ideas were there in the 80s and the 90s. So big data is when your training requires huge amounts of data. Now, these machines are making all sorts of decisions. When you go to a bank, they are using this in order to make decisions, self-driving cars, and so on and so forth. So it is actually quite important for us to start asking ourselves, are these machines rational? And if they are not, what is the implication of this in their deployment? We do know that much of these machines, especially deep learning, is not transparent. It is transparent, but it is not interpretable. It's transparent because you can see all those activation functions. You can see the weight matrices, but you cannot be able to say the reason why, if you go to a bank and you want a loan and they put your details on an algorithm and it says no. If you go back and say, please tell me, why are you denying me the loan? You wouldn't be able to look at those weights and be able to explain why you are being denied the loan. It's not easy, And of course, as we move forward, we'll need to think about transparent AI, not transparent interpretable AI. So linguistically, rationality is the art of making logical decisions. It manifests itself by the concept called the maximization of utility. I think this is actually quite an important point. There is a book written about 200 years ago called Utilitarianism. You should read it now. It's probably the first book that introduced the concept of maximizing utility. And utility is basically the usefulness of whatever you are trying to do. So when you are training a multi-layer perceptron by minimizing the error, which, by the way, is completely equivalent to maximizing your predictive capacity, you can think of it as a utilitarian concept. So, and rational decision-making, therefore, is the use of complete data, very, very important, which is processed with a perfect biological or a physical brain. It can be a neural network, in an optimized fashion to make a decision. Given this definition, how many of you think that we can realistically achieve a rational decision as human beings? None. Thank you very much. Now, let me just give you a very simple question. Suppose Minister Tito Mboweni wants to decrease government spending. He has two options. One is to reduce government workforce. Option 2 is to consult a Sangoma from Dutuni. I am from Dutuni village, and the war knows, and our Sangomas are very, very good. Who gives him a condition called Mudaka to drink, and this will reduce government spending? Which option do you think he should choose and why? 2. 1. If somebody chooses option 2, would you agree with me that this person is irrational? Because he's using information, but it's irrelevant information. So relevance of information is very, very important. Completeness of the information is also very important. Suppose Sipho is presented with 2 choices to fly from Johannesburg to Frankfurt. He should fly from Johannesburg to Addis Ababa to Moscow to Paris to Frankfurt for no other, and at the cost of 100,000, for no other reason except the fact that he wanted to move from Johannesburg to Frankfurt. Option 2, he should fly from Johannesburg to Frankfurt directly at the cost of 13,000 rand. Which option should Sipho choose and why? Option 2. Why is option 2 preferred over option 1? It's because it optimizes. So optimization is one of the criteria of rationality. The previous example shows us that relevant information is another criteria of rationality. Now, Herbert Simon proposed what is called bounded rationality. I think this is what he won a Nobel Prize for in economics. I can't quite remember what I think he won for being one of the pioneers of AI, the Turing Award. He observed that information is almost always imperfect and incomplete. He also observed that we actually do not have a perfect brain to process information. Human beings don't have that. There is a book written by Kahneman and Tversky. It's called Thinking Fast and Slow. How many of you have read Thinking Fast and Slow? What is 2 plus 2? 4. Everybody can tell, isn't it? What is 91 times 73? Anybody who can tell me, please raise your hand. None of you can be able to tell. So what Kahneman and Tversky found out was that the way our mind works, it works in 2 ways. He calls one system 1, which is automatic when I say what is 2 plus 2, and it is fast. And the second one is when I asked you 97 times 71, it's reflective. You will not be able to answer that question without either punching on a calculator or doing some form of calculations. So you have to reflect. So, and this is slow. That is why the book is called Thinking Fast and Slow. And we'll talk about what happens when you migrate decision-making to a machine. He also observed that we do not optimize, but we use heuristics and biases. He spent a lot of time, he won a Nobel Prize for this, so he spent a lot of time studying this. He will ask people and you will realize that their answers are wrong because they don't even do detailed calculations. They anchor, their answer from the information that they have. So he called all these limitations. He therefore concluded that because of all these limitations, unbounded rationality does not exist. So rationality is always bounded, and bounded means it is limited. Now, how do machines make a decision, a rational decision? So you will have a piece of data. You will have your model, and from your model you will make a decision. You might have a feedback that goes into the model, and the feedback might actually go back to the data, that maybe you are not collecting enough data, please collect more, or your sensor doesn't seem to be right. And these things, by the way, we think they are actually quite, theoretical, but they are practical. One of the reasons why Boeing 737 MAX collapsed was a combination of two things. Number one, the pitch data seems to have been faulty. Number two, the control model actually was not working too well. Number three, we don't really understand stability. If you go to control systems and you study stability of classical controllers, you can be able to get Ruth Hurwitz and you can be able to get stability regimes. But when those models become AI machines, stability is not understood. Probably it will have to be estimated. It probably cannot be calculated. So this is a rational machine, how it works. Now, if we come now to an easy system here, a multi-layer perceptron, you have set of inputs and set of outputs. So the output will probably be the decision that you're supposed to take, and the input is the data that you collect. Again, we have built these machines. I'm not going to talk about, you all know that this can be represented by that equation. It's quite simple, isn't it? It is quite simple. And to train the network, you just need to construct an error function and find a derivative. And then your conjugate gradient method will be able to do this. But now, what is wrong with this model? There is a British statistician called George Box. How many of you know Box? George Box. Yeah. He is famous for saying this statement: all models are wrong. All models are wrong, but they are useful. And many people were arguing, but why are you telling us that all models are wrong? Says, I'm telling you that all models are wrong precisely because many people think models are right. So I think it is very, very important for us to contextualize that no matter how good the models are, they are mere estimation of reality. They are not reality, and therefore they are wrong. Now, if we are going to build machines using the concept of models, how can something that is wrong, we agree it is wrong, be rational? Those are the questions that we need to ask. By the way, if you need more details on this, there's a book called Handbook of Machine Learning that I author. Please go and buy it. It is on Amazon. Now, how can we use such models to try to make rational decisions? This is the work that I did with Monica Lagazio 15 years ago. So this is a book that we wrote. Can we ever be able to predict whether two countries will go to war or not? People go to school and they train as political scientists to be able to make such decisions. And of course, this has all sorts of implications on how we should train social scientists. So what happens here is that this is the book that we wrote on this with Monica. So what happened was we used data. So you have this thing called militarized interstate data. So it has 1 million entries. It's a combination of relationships between all sorts of countries over 70, 80 years. It looks at the distances between the two countries. It looks at the difference in the degree of militarization between the two countries. It looks at the number of treaties that are shared by the two countries. It looks at whether the two countries share a border or not. And then it tells you whether, given that particular state, at that particular time, whether the two countries were in conflict or not conflict. And what we were doing was to do this and use deep learning to be able to make predictions as to whether two countries are going to go to war or not. How many of you here think Lesotho and Switzerland are going to go to war? You can almost see why, isn't it? Small countries, one is completely enclosed by one country, the distances between the two. So that was actually, and we were able to build different types of artificial intelligence. At that time, support vector machines was the flavor of the day, and we were able to do this. And we wrote a book. What was interesting is that the Chinese military translated the book into Mandarin. So I was quite interested to know, how does Marwala get spelled in Mandarin? So this is how they spell it. The first character, Ma, means a horse. That is how you write Jack Ma. I'm serious. That's how he writes it. And the second one is a gutter of a roof. You can see a cap on top and something that is almost collecting water there. Is Wa. And the third and fourth character is La. It means to pull, and so on and so forth. So again, this is not perfectly rational decisions that we're making, but the decisions that such a machine makes is certainly more rational than the decision that a political scientist would make in trying to solve this problem. This is the work that I did with Shakir, one of the founders of deep learning. This must be 20 years ago, So this is the detection of epilepsy. And the reason why we became interested in this is that next to where I live, there is a hospital called Tshilidzi Hospital. My name is Tshilidzi. I'm not lying, Tshilidzi Hospital, It was not named after me, by the way, And every time you go there, you see long queues of people. They cannot be able to see a doctor because they don't have enough doctors. And we started thinking about, is it possible for us to be able to use, because these technologies are very, very cheap. And EEG signal is quite cheap, and then you can graduate a nurse to be able to make some sophisticated diagnostics. Again, and we did some work where we asked trained doctors to be able to make diagnoses like this, and we stopped. We finished and we stored the information. 3 months later, we asked the same doctors, same information. Half of them changed their minds. Now, when doctors change their minds, it is called misdiagnosis. It means somebody who had epilepsy was obviously told that you can go home, you are fine. And somebody with epilepsy, without epilepsy, was given medication. So that's another example of the work that we did. Again, it is bringing more rationality. It's not perfect rationality, it's bounded rationality. And we'll talk about what it actually means to the theory of bounded rationality. This is another work that I did with Simon Scarrell, detection of pulmonary embolism. Again, you see, before the advent of deep learning, there used to be something called pre-processing. Still remember that? And of course, by the way, the disadvantage, what I don't like is that we forget the fundamentals. Now people talk about convolution without actually understanding it mathematically. I mean, if you go and start doing Fourier transform, that is convolution mathematics, isn't it? How many of you still remember what Fourier transform is? I'm impressed, but people are forgetting about this, And of course, the argument is that deep learning does the convolution. Whereas when we did this work, we were externally doing a convolution. So you will take your data, and then you will do a Fourier transform, and it will give you frequencies. And based on that, you will take it to a machine, because the machine did not have 10,000 inputs. It will have reduced inputs, and it still did quite well, obviously. So this is another work that we did. I did this with Dr. Busisiwe Vilakazi. Usisiwe was my master student. She's actually on the ESCOM panel. She went on to do a PhD in AI at Oxford University, DPhil, they call it, doctorate in. And this was, can we be able to predict whether a building is about to collapse or not? And this is, how many of you know this bridge? This is in Johannesburg. It's called Greystone Drive. It collapsed. So the question is, could we have used AI to be able to prevent this? My grandmother, and I write it in this book that I wrote, was my first engineering teacher. She used to make clay pots. So I used to accompany her to go and look at clay. And of course, clay is always found next to the river. For those of you who do not know, it has to be a wet environment. And we'll go there and she will select the clay. Later on, when I was studying engineering, they call that process of selection material selection. Give it a sophisticated word. And then she will come and then she will make the pot. It's a complicated 3D thing that is almost round, but it is not completely covered, because you have to have a hole so that you can go to put food inside, you know. And then if we ask young people today to do that, they will be thinking about AutoCAD, computer-aided design. She did not know what it was. And after that, she will take it to the sun to cool to basically dry it. And after it is dry, she will take it. She will not go and cook with it because it's going to break, isn't it? You know? She will take it into the oven in order to bake it. And then she will allow it to cool slowly. That process of cooling is called annealing. There is an optimization technique called simulated annealing that uses that. You know. My grandmother did not know what annealing was, but she knew that that thing must be cooled very, very slowly. For those of you who have worked with simulated annealing, you'll know about cooling schedules and so on and so forth. And after she has cooled it down, she will knock each pot and listen to it. If it rings for a long time, it's a good pot. And of course, for those of you who study mechanical engineering, if it rings for a long time, it's a lightly damped structure. If it rings for a short time, it's a bad pot because it is damped. Maybe some fluid is trapped inside, you know, and it will crack very, very quickly. But what really worried us was that as she was growing old, she was disposing good pots. Anyone knows why? Her hearing was deteriorating. You see, rationality actually deteriorates as you age. No, I should know. So, and then what we did here was to say, no, how can we take that whole process and put it into the fourth industrial age? So all you need to do now, you use vibration data. If you go and knock a structure, it excites all the frequencies. And you can be able to use that data. Maybe you do some form of pre-processing. I like to do pre-processing. And then you put it on a neural network, and it is able to tell you whether that pot is good or not. And of course, the power of using machine learning to be able to do this is that it can be able to estimate even the strength of your pot, something that your ear would not be able to do. So again, this whole process of modeling, even though the models are wrong, but they are useful, is actually bringing us closer to rational decision making. This is another example of the work that we did, something called finite element modeling. Do you know something called finite element modeling? So this is a finite element model of a bone, the finite element model of somebody's dental system, a finite element model of a car. The problem is that these models are very, very complex. For the car, you are talking about 1 billion by 1 billion degrees of freedom matrices. I mean, just getting the first 10 eigenvalues is absolutely, it's just computationally very, very difficult. But the biggest problem is that what the finite element model predicts and what actually happens in real life actually don't talk to one another. So you have something called finite element updating, which is how do you make your finite element model predict what it is observed. It's almost like learning, isn't it? So you will write some fitness function between model prediction and the data that you have measured. You will have some certain characteristics of the model that you are not sure about. So you improve them, you update them using some form of optimization. You can even use Bayesian statistics to be able to do this. The likelihood function obviously is going to be derived by the distance between your model and your prediction. Your prior, maybe, your model is not that wrong. You assume that you are in the ballpark, and then the data is what you collect. This was quite an impressive piece of work, which we actually wrote 2 books around this one. By the way, these books, please go and buy them. So this is the work that I did with my student. Dan Golding now works for Discovery in London. So this is the system called a triage. It was invented in the army. So what we really wanted to do is that when you go to a casualty ward at Chris Hani Baragwanath, you always have more people who need medical help than doctors. Now the big question is, who do you help first? Second, third, fourth, so that you can be able to maximize the survival rate. So that was the system that we did. We used a bit of reinforcement learning here to be able to do this. We also used something that in this community, some of you might jump up and down, genetic algorithm as an optimization. And the reason for that is because, the reason why we chose this is because, I suppose you could have done Bayesian estimation, is because you don't have closed form solutions. You cannot be able to calculate gradients. So as a result, you just needed to estimate to get something that could actually work, and it works, So that is another example of the work that we did. The other work that we did in this area is creating something called the artificial larynx. So somebody loses their voice box, normally because of cancer. So they remove the voice box, but the person can still move their tongue. Can we be able to look at the movement of their tongue and be able to predict what they are supposed to say? This was an article on the MIT Technology Review that was talking about this invention. It's called a robot. They call it a robot voice. We called it an artificial larynx. So this is the device that you put in your mouth, and then this is how it looks like. Ultimately, the movement of the tongue is translated into data, which is at the bottom. And that data, you train it, you know what the person is saying because you have to record all these things. Somebody says, come here, and then you record it based on the movement of the tongue, and then you for each signal, there is a corresponding word that is said. You can synthesize that word, and then we actually use multi-layer perceptron. It works quite well, and this was a patent that we received in this regard. The last, one of the last work that we did before we go back to rationality is that problem that I talked about. Because what we are forgetting, and this is what really worries me about the development of machine learning in the continent of Africa. We are following too much what people outside are doing. Firstly, our data is never complete. Secondly, sometimes it is just bad data. And the concept that we have, the assumption that we have all the data we want, almost does not hold in our context. And we are forgetting how to make decision-making with incomplete information. How many of you still remember expectation maximization technique? Yeah, I mean, it's about 5. Which probably was the algorithm that was developed to handle missing information, you know. But our problems, if we are going to build these medical devices, we should always assume that the data that is going to be presented to us will almost be incomplete. So this was the work that we did in order to deal with that issue of how to estimate HIV and therefore prevent somebody from going to go and test. So we went to the Department of Health. They gave us this antenatal database. But the problem with South Africa's antenatal database is that it is almost incomplete. One of the variables that was always missing was the issue of the father of the unborn child. Sometimes it was not there. And we asked why. You know, sometimes if it is a 21-year-old and the father is 75 years old, you probably will not get that figure, you know. So there were many reasons why. So in the literature of missing data, you have various forms of missingness. The easiest to handle is missing at random. If something is just missing at random, you probably can get away with an average estimation. If you just take the average of that particular variable, you probably will be fine. Then you can have systematic missing, like, you know, a sensor has just died. So all of a sudden, nothing is actually being recorded. An average does not work there, because maybe the regime, the operation conditions are no longer identical. You are no longer flying at 500 meters above ground. You are flying at 1 kilometer above ground. So we spend a lot of time trying to build a model that will be able to deal with issues of missing data. And the model that we use is what is called the autoencoder, auto-associative networks. How many of you know what an auto-associative network is? Basically, it is a network that is trained to recall what it has seen. So the input and the output are the same. Sounds quite useless, isn't it? Why would you train something to recall what it has seen? Now, if you give it something that is incomplete, and you randomly estimate that missing information, what do you think is going to happen if your estimation is wrong? It will not be able to recall the complete database, isn't it? So you can use some form of optimization to be able to identify the missing values, so that every time if you give it the complete data, it will be able to reproduce it. So that is really the work that we did. So this was the work that we did on reinforcement learning. We're designing software agents that work quite independently. And this one was playing quite a simple game called a poker game. And one characteristic about a poker game is that bluffing is a strength. If you can be able to bluff, you probably can play poker quite well. So what we found here, we did not train it to bluff. It learned how to bluff through reinforcement learning. And it was able to do that. This was in 2007. It appeared on New Scientist. Some people thought we were bluffing. They thought we were bluffing, and we are not bluffing, and I am not bluffing. So again, the second conclusion that we reached here was that it was with my student Evan Hurwitz, who now works for Standards and Poor in London. Is that bluffing is actually a rational activity that it is done in order to maximize the future rewards, and for the poker game, a win. Now, going back to the theory of bounded rationality, artificial intelligence machines are now making decisions, as I have indicated, whether it is in the medical domain, whether it is in the estimation of whether a bridge is going to collapse or not, and so on and so forth. And machines have systems 1. If you give a machine 97 times 71, it will answer as quickly as it will answer 2 plus 2. Human beings are not supposed to do. They are not able to do that. In other words, machine decision-making, unlike human decision-making, uses only system 1. Whereas human decision-making uses system 1 and 2. Very, very. And this system 1 that it uses is actually becoming better. So if you create a deep learning algorithm that is supposed to solve a particular problem today, 2 years from today, it does it more efficiently than today, for the simple reason that computational power in 2 years' time is much better than now. So the whole principle of Moore's law is making machine decision-making fast and faster, as opposed to fast and slow for the human being. And thirdly, machines can optimize. They are able to identify that utility, that best utility. They can be able to optimize. Of course, that is not quite true, because there are 2 types of optimization problems. The first one is what you call a convex optimization problem. How many of you know what a convex optimization problem is? How many of you can test for convexity of an optimization problem? Good. Well, I would be interested to know, But most of the problems are actually non-convex. Non-convex basically means that when you identify an optimum solution, you don't know that that is a global optimum solution. You have no ways of knowing whether this is a global solution if it is non-convex. This means the whole concept of machine decision-making, we can only be sure of its rationality if the optimization process is actually convex, not non-convex. The missing data estimation, data processing is making this decision better. So you can be able to complete things that are not really complete. The idea of complexity of your model and dimension of your data, we don't really know. It's all subjective. There's no scientific way of doing it. When you learn in AI, they teach you of something called Occam's razor. You know something called Occam's razor? It basically says that the simplest model that describes all your observations is actually the most likely to be the correct one. It doesn't say it is the correct one. It says it's the most likely to be the correct one. So given all these things, the bounds of rationality are flexible. They are flexible because once your computational power, once Intel produces a new chip, your bounds move, because now you have machines that are quite fast. And of course, this will continue until we reach a Moore's law limit. And perhaps we'll move on to quantum computing. And when we move on to quantum computing, then we will have quantum Moore's law. So that is the thing about this. Now, this is a beautiful figure that me and Evan Hewitt produced. It's beautiful, isn't it? So what you see here is... can you hear me? Doesn't seem to be working. Can you hear me? Okay. You will have to look back. So the bounded rationality there is the limit of rationality, which no amount of technology will change, will improve. Then prospect theory, which is what Kahneman and Tversky produced. Kahneman won a Nobel Prize for that. This is now the bounds that are prescribed by human beings, human behavior. The best human being to make you can create it by finding the best human being to make that particular decision. Somewhere in between the ultimate bound and the prospect theory. That is where artificial intelligent decision-making is. It's not the best we can, simply because the models are not perfect, but it is better than human beings. So you can pretty much conclude that machines are more rational than human beings. Now, this is another concept of rationality called rational choice. Rational choice is a theory that economists like to use. A recent graduate was offered these two jobs. Option one, take a job at Microlife, not to be confused with Microsoft, and get paid 80,000 rands per month. Or take a job at Deep Thought, not to be confused with DeepMind, and get paid 2,000 rands per month. Which option should she choose and why? Option one, why? Because option one gives more utility than option two. So the whole concept of choosing option one over option two is what is called a rational choice. Of course, when I offer this, I'm making few assumptions. I'm making one assumption is that these are the only options available. There might be other options that are available. I'm also making an assumption that other factors such as work-life balance do not matter, because you can choose option two if, half of the time you are on holiday, or maybe it gives you much more prospect for traveling, whatever that is. But how about if option one and option two gives you identical utility? And by the way, this is not too far-fetched. Robots are basically, they reach a point where they have to make a decision, and the utilities that is presented to the decision-making processor are identical. What do you do? Well, maybe you can randomly choose. That's probably the best way of getting out of it. The whole concept, a robot has to choose one or two paths with the same utility. The choice of one over another is obviously subjective if they give you identical utility, isn't it? If option one is better than option two, then choosing option one is a rational choice. But if option one and option two gives exactly the same identity, choosing one and foregoing two is basically random. How about if you have multiple objectives, multiple objective utility? For example, at ESCOM, part of the reason why we have a problem is that you have the commercial dilemma, which wants to maximize profit. You have the maintenance dilemma, which wants to maximize the availability of the plant. And then you also have the technical dilemma. To get the best engineers, everybody to be a best engineer, and so on and so forth. Now, how do you deal with multi-objective optimization? The whole concept that you can be presented with two options with identical utility basically makes machine rationality subjective. That is the first conclusion that we reach. So this is the thing. The multi-objective optimization. So if you are presented, I know people in machine learning, you don't really deal a great deal with multi-objective optimization. So if you have objective one and objective two, there is no rational way of weighing which option is important over another. So what you do in optimization, you plot something called a Pareto frontier, which basically saying, you start by saying that if objective one is the most important objective and objective two is not important, what is the optimal point? And then you obviously weigh differently until you have this frontier. So at any point on the Pareto frontier, you are optimizing. But your optimization is basically subjective. You can be at any point. So that is the second reason why rationality is subjective. Then you have something called counterfactuals. The concept of counterfactuals is very, very important. The whole concept of clinical trials is really about the estimation of counterfactuals. So if you have a piece of medication, which if you claim that if you administer it, it will cure, let's say, a headache. The only way you can be able to do that is to identify a subject, and you give them the pill and see whether they're going to be healed, and not give them the pill at the same time and see what is going to happen. So you are trying to estimate causality. It's physically impossible, isn't it? You can't give somebody a pill and not give them at the same time. So what statisticians have decided, they have discovered something called a control experiment. A control experiment, you want to create as much identical conditions to the one where you are going to administer a condition as possible. So basically, it is all about estimation of counterfactuals. Now, there are many counterfactuals out there. And by the way, counterfactuals is an important concept in psychology because they say depression is caused by, some form of depression is caused by people saying, if only I did not study engineering, I studied psychology, I would have been much better off. It's called, you are creating counterfactuals in your mind. But that doesn't really matter, you know. But there is a certain type of counterfactuals called rational counterfactuals. For example, you are at a chemical plant and there is an explosion. And what you would like to identify is a counterfactual, which is to say, what should I have done in order to minimize the chances of that explosion happening? So that is a rational counterfactual. Now, lastly, the concept of machine rationality, group versus individual rationality. If you are on the if you choose different, if a voter is maximizing their own utility and they are at the Pareto frontier, if you combine rational voters, does it necessarily mean that you're going to have a rational outcome? A combined rational outcome? Yes or no? No. No. So, and by the way, that is why classifiers, voting classifiers, are not necessarily the optimal way of combining classifiers. You normally would combine them at a regression level and only convert them into ordinal numbers later. Now, to answer the questions that I posed at the beginning, can machine be rational? Yes. But that rationality is flexibly bounded. Can rationality be measured? You know, to a certain extent, because you probably can be able to estimate the completeness of information. You can probably estimate ultimately the measure of how rational a machine is by how much error it makes. The generalization error is a measure of rationality of that machine. Is machine rationality subjective? Yes, it is absolutely subjective. It is subjective because of the multi-objective nature of the problem. The formulation of the utility might also be problematic. Now, this is just a comparison between human rationality and machine rationality. Humans are risk averse. Machines are utility maximizers. Humans, they are completely bounded rationality, prospect theory, whereas machine rationality depends on what technology we are deploying there. Human beings are obviously irrational because of biases and heuristics, whereas machines are, flexibly bounded. Human beings only think of counterfactuals, but machine can be able to think of rational counterfactuals that estimate the occurrence of something. Human beings use systems 1 and systems 2, fast and slow, whereas machines use systems 1, which is fast and faster. Now, if I were to explain this in terms of diagrammatically, if we look at data and an AI system as a single system, your first problem is imperfection and incompleteness of your data. That is the problem that you will have to deal with. The second problem that you will have to deal with is the issue of hacking. Is there a possibility that somebody can be able to hack into your system and change the weight of your machine, and what is the implication of that? So it can still be, the model that is in deployment can still be interfered with. The estimation errors is another issue that you need to deal with. If we go to a human being, of course, the information that we perceive is still imperfect and incomplete. Biases and heuristics are a big problem. Information overload. I was reading somewhere that, before, if you wanted to control people, you denied them information. Today, you give them too much information so that they are so confused. That gets you thinking. Because if you look at the political era of the past, the Soviet Union, the way they used to manage people, they used to manage flow of information to the denied population. But the outcome of somebody being denied information or being given too much information is almost identical. It's confusion and inability to make decisions, rational decisions. So the AI system is more endogenous. The factors that can influence it, you do have exogenous factors, but you really need to worry more about things that are inside the data and things that are inside the model. Whereas for human beings, you should be more worried about outside factors. Those are the issues that you need to worry about. Now, we apply this whole concept of rationality to the problem of the financial markets. Now, the stock exchange is an example of a financial market. And the stock exchange is said to be rational or efficient if it is able to absorb all the information that influences it. It's called the theory of the market, the efficient market hypothesis. That's what it is called. Of course, rational markets are efficient, can be efficient if you optimize. But the problem is that when you go to the stock exchange, human behavior is part of the stock market. And the reason for that is because human beings are still making decisions as to whether to buy or sell particular stocks or not. The second concept is called information asymmetry. The idea that one party knows more information than another. basically makes the whole market inefficient. If you remove humans from the stock market, which is happening by the way, and in their place you add an AI decision maker, it actually makes the market more efficient. Do you agree with me? And by the way, it is not just the idea of the market being changing, but also the principles that drive the market are also changing. So we have studied quite a few number of issues that are changing in the market. The concept of demand and supply is changing. And not too long ago, we went to Amazon, me and a friend of mine in Brazil, and we bought the same book at the same time. We got 2 different prices. Do you know why? Because Amazon takes all your information and study your buying patterns. And based on that, it is able to do an individualized demand curve. And my demand curve was different from the demand curve of my friend Fernando. And as a result, the prices were different. By the way, it is not too far off. If you go to Southeast Asia and you go to a market, you normally get the price you deserve, isn't it, Tina? And the reason there is very, very simple. The seller basically estimates your demand curve. And based on the demand curve, they give you a price. In many parts of those markets, your way of negotiating a price should include physically walking away. You physically walk away, and then if they don't follow you, then you probably wander back, with a new price until they follow you, So the whole field, the practice of economics is changing. Credit scoring is becoming done by machines. But the theories of economics are actually now also changing. So this is a course at Cornell University called Networks. And the reason why I'm putting this is because they actually took our theory on information asymmetry. We did not invent information asymmetry. All we did was to say, if the buyers and sellers are no longer human beings, but they are artificial intelligent machines, and we did a simulation, what happens to the concept of information asymmetry? Information asymmetry was the work that was done by 3 people who won a Nobel Prize in the 70s. Stiglitz was one of them. So they used the concept of 2 car salesmen. So you have 2 car salesmen. One sells very, very good cars. Another one sells very, very bad cars. And you as a customer does not know which one is which because of information asymmetry. And they were asking what will happen to these 2 car salesmen. And their conclusion was that the good car salesman will actually go out of the market. He will become bankrupt. So, but why would he become bankrupt? If the reason is very simple. He knows his cars are good. He's less likely to give a discount than a bad car salesman. Now, if we were to put AI machines into that transaction, it can be able to go to the internet and look for information and so on and so forth. What will happen to the concept of information asymmetry? And our conclusion is that AI can greatly reduce the level of information asymmetry and thus enhancing the efficiency of trades in the market. The second conclusion that we reached, which was quite counterintuitive, is that as you decrease the level of information asymmetry in the market, the volume of trades actually decreases. Why? It turns out that the reason why people exchange goods and services is because of information asymmetry. if you have 1,000 rands and I have my phone, for me to give you my phone for the 1,000 rands, the 1,000 rands must be more valuable to me than a phone. And for you to accept my phone in exchange of 1,000 rands, that phone must be more valuable to you than 1,000 rands. If that information asymmetry does not exist, then those goods and services will not be exchanged. So that is an example. This is, I actually got this in a German newspaper, and this really worried me quite a bit. For those of you who can read German, you can be able to understand. This is the work that I did at the University of Johannesburg. So they basically write everything, and they do mention University of Johannesburg, but they mention Cambridge. That's not what I did when I was at Cambridge. I think this is quite an important factor, that when our universities do things, we normally try to find outside explanations of why. I don't think that is right, Because this was probably 2014, 15 years after leaving University of Cambridge, and I've only been there 3 times ever since I left, So, which means that the work that we do, we should actually highlight. We should be proud that we are doing good work here in South Africa, and encourage people to use our local affiliations, so that in the future they can be able to trust that whatever we have come up with is not because we went somewhere else outside the country to be able to do these things. So thank you very much. I thought there was volume, but there's not. Okay. In summary, I was on CNN talking about artificial intelligence. Nyawonga, thank you very much.
My name is Tshilidzi Oliveira. I'm a professor here at UKZN, and I run a genomics center. So very happy to hear that you think that genomics and biology should come together. One thing just to ask from the panel in your talk, that just to be kind of thought-provoking, what is our scientific advantage in Africa on artificial intelligence? Yeah. How can we develop that? And how can we stop, especially computer scientists, to fuff around? I'm a bioinformatician, and a lot of time people spend a lot of time doing things that is not important or don't have a big outcome. So just my question, what do you think that's our advantage here, and what should we develop in artificial intelligence?
I think our big advantage is the problems around us. The problems around us are actually quite complex. One of the work that we did, I did this with a gentleman called Mashawa. He died last year. Quite sad. Young man, he went to work for McKinsey for many years, and he had just started his job at Amazon in Cape Town, and he just died. So what happened was that in the 90s and the 2000s, there were lots of Cuban doctors that were working in our hospitals. So we were very worried about the translation between the doctor-patient, And in such a relationship, you want to avoid a third party, because there is confidentiality, isn't it, So what we were trying to do was to create an automated machine translation from English to Sesotho sa Leboa. That is the language that is spoken in Limpopo. And we work with these things, and it worked quite well. You can be able to use Sesotho sa Leboa expressions, and they will be translated into English, and it can also be continuous speech. Because if it is machines are able to deal with words much easier than they can be able to deal with a speech. So if you say a dog, mbya in my language, it probably will be able to translate that. But if it is part of an expression, a 3 minutes conversation, it gets confused. You cannot be able to tell the distance between words and so on and so forth. So it worked quite well. And we tried to do this in isiXhosa. That was when our problem started. Every time there was a click, it thought it was noise. And if you look at the isiXhosa speech, it's like this, then something up, and then we went back and studied linguistically what is actually going on. We found out that no, isiXhosa is not one language, it's actually 2 languages. You have a family of languages that are spoken all the way from South Africa to Tanzania. They are called Bantu languages. isiXhosa is one part of that. That is the non-clicking part of isiXhosa. Then you have the clicking part, which is at best 7% of the language, at best. Normally when somebody says they speak isiXhosa, we think of clicks. But statistically, it's not a clicking language at all. It's only 7%, Now, and the reason for that is because they borrowed the clicks from Khoisan. And Khoisan and isiXhosa are completely different languages. They are not even same family of languages. Now, the fact that the clicks are only 7% basically makes it, it's actually quite, normally languages tend to be similar in the same geographical space. It probably talks about the migration of Bantus from Central Africa and their introduction in South Africa, which was obviously quite sudden. Now, the question that we were asking is that, does this not require us to develop new algorithms? I think it does. So our advantage is to solve our own problems. If you go to Google Maps, it cannot, normally I cannot hear it when it pronounces African names. I just can't. Miriam Makeba becomes Miriam Makiba. It's not even the same. Not too long ago, I got a Google assistant. That useless piece of device. So I said to it, who is Tshilidzi Marwala? That's my name. It cannot be able to hear me at all. I can tell you, it probably heard my name maybe once ever since I bought that device. It just can't hear it. So I asked it, so who is the author of Skynet in the market? It pronounces my co-author, Evan Hewitz, quite well. Tshilidzi Marwala is like an American accented, incomprehensible expression. And I have really tried to imitate it, but I just cannot be able to do it. I succeeded only once. Again, why aren't we developing our own devices that deal with our own language? If you think it is only voice, then we went to a translation of isiZulu words on Google Translate. And for those of you who has Google Translate now, you can go there. And then I give it an expression. Akwehlanga lungehlanga. That is when you are giving somebody condolences. You just write it like that. It interprets it as race does not matter. Not even complete. I mean, I would have thought text to text, translation will actually be quite good, especially if it is being done by a company called Google. It turns out that it is not able to do that. But if you translate from English to isiZulu, it's more accurate than if you translate from isiZulu to English. This concept is an old concept called the principle of reciprocity. I think it was a Jewish rabbi called Hillel who came up with that expression. The fact that, the translation from English to isiZulu is more accurate than from isiZulu to English. It's quite mysterious, isn't it? The reason for that is because the person who actually designed this thing is an English speaker, not isiZulu speaker. Again, can't we create our own? Because these are not complicated things. You just need a dictionary, and maybe you just need old people to be able to tell you the dictionary is not a difficult part. It's piecing things together, because it looks like this was done from a dictionary, word by word. Whereas when you piece things together, especially in African languages, the meaning is not direct, The words no longer matter because the combination means something else as compared to the individual words. Again, so our advantages is actually solving our own problems.
Right. Thank you very much for the talk, sir. I just want to ask two questions. The first question I want to ask is about the bounds of human rationality. So in your talk, you said the human rationality is bounded compared to the flexible bounds of the machine rationality. So I just wanted you to speak to that a bit more in terms of humans. Does that mean that human intelligence cannot improve over time? Since if you're saying that it's bounded, then that means maybe it cannot improve over time, I think. So I just want you to explain that a bit. And then also, with respect to imputation, so of data missingness, I just wanted you to also speak to that in terms of, the fact that when you input data, it doesn't really introduce anything new per se. It just helps maybe that you're just trying to represent the model of what exists. So how do we deal with that? And then finally, if you would, I'm sorry, but then we're talking about artificial intelligence and the movement of how fast and this thing. And then the panel talked about education. So I wanted you to also speak to interest. Because when we're talking about people being taught more about maybe coding and all these things, tech and all that, how does interest play into that in terms of the people not being interested in doing it?
Look, you actually hit the nail on its head. I'll take one by one because I am not writing anything. When you said that missing data estimation does not introduce anything new. Machine prediction, deep learning prediction does not introduce anything new. It's basically y is equals to fx. It already exists. You take f already exists is your model, x is what you have observed. You're just rearranging information that actually exists. Prediction is nothing but rearrangement of the facts that already exist. And that is why this concept of all models are wrong is so powerful, because we forget that. That is y is equals to fx. The x is your observation, it exists. The f is your model, it exists. But somehow, out of two existing things, you get a y, and people think y is a new thing. It's not a new thing. It's an old thing, So prediction is nothing but a rearrangement of information that already exists. And that is why, if something out of the ordinary happens, these machines does not work. It can't work because it is not part of your training data. It's not part of the information that you had before. You probably have to look at other phenomena of modeling the problem. Very, very important. In terms of the bounds, I don't want to, basically, human beings, we are what we are because we have evolved to be who we are. So we're not 5,000 years old. We have been here for millions and millions of years. So now what happens is that many of the things that we have are characteristics of the evolutionary trajectory that we have undergone. The idea of risk averse of human beings is so embedded on us that if something just fall here, you will just flee instantly. Because those of our ancestors that saw lions and ran to them in bravery were eaten by those lions, and their gene pools never got the opportunity to reproduce. So this risk averse is so embedded in us that whenever we make decisions, we are risk averse even in circumstances where we are supposed to optimize. Because of that, we are naturally irrational. And by the way, this has been written quite extensively about human irrationality. And now the function of getting a mathematical equation to rearrange the information that already exists is basically meant for us to now think logically. The new thing that comes out is logical thinking. In fact, it's not even logical thinking. It's basically using machines to augment our decision. Now, when it comes to our ability to think, our brain is a hugely capable machine. We only use 10% of it at best for thinking. So I don't think bounds you should actually relate it to rationality. Rationality here means consistency, means using all the information. Because human beings, if I give you 100 variables to use in order to make a decision, you can't use it. You will not be able to use it, even if you want, because you will never evolve to be able to take 100 variables to make a decision. But if I give you one variable and say, if it is cloudy, when you go out, take an umbrella, because it might rain, you will be able to do it because we are able to handle single variables much easier than we are able to handle multiple variables. But obviously, using multiple variables actually gives you more information. Now, the last one, in terms of interest. You see, that is why universities are very important. And it's linked to the question on the viability of university systems. We never know if we had to learn things because we are interested in them. We will never be effective intellectuals. We can't. Because to be effective requires you to use knowledge that you might not necessarily be interested in. I was not interested in acting, but I took it. And I enjoyed it. And I acted on My Children, My Africa, and I was given a prize because I was acting very, very well. I did not know it. It's only after the fact that I realized that I actually enjoyed it. By the way, I also took 2 psychology classes. I did not like those multiple choice examination problems. That's why I dropped it, But I did pass it well, I just did not like that thing, So there's something about education that should be decoupled from interest. Because human beings simply just do not know what interests them or what does not interest them. And in fact, whatever course you're going to take, there's always going to be material that you will have to learn that you are not interested in. Yeah.
Tshilidzi, fascinating talk. In terms of your key questions, you mentioned, can rationality be measured? And I'm just thinking, I'm actually looking at a framework for trustworthy AI. I'm going to talk about it tomorrow as well in my talk. But I don't see rationality. I don't know if you've seen the European Union has got an ethics guideline for trustworthy AI. Have you seen it?
Well, I know about GDPR.
Yeah, but that's GDPR, but they just recently launched the ethics guideline for trustworthy AI. What's interesting there, they talk about 4 ethical principles, they talk about 7 key requirements, but what I don't see here is rationality. And if we can measure that, I think it's an important thing to bring in. So I would love to discuss this with you afterwards as well. But it's fascinating. Thanks for a brilliant talk.
Thanks.
Hi, Professor. Great talk. And I must say, this is one, because I'm coming from industry, from PwC. I work for the Cognitive and Intelligent Automation team. And this is one concept I may say is very mind-blowing, because when we think about artificial intelligence, the idea of rationality, has never featured much. And it's very interesting to hear about, this being taken into consideration, because one thing that speaks to us is about, responsible AI. And because companies are now looking to adopt more AI solutions, how do we now drive towards, embedding more, responsible AI and making sure that AI is not used just for, capitalism or nefarious use, just to be used more to, come up with useful solutions to the market. So in my mind, or one question that also comes to me when you mention about rationality. So most of these models, when they are built, obviously it's built by human beings for one way or another. So do we distinguish between bias and rationality? Are those two completely different concepts, or do we somehow think that if you do deal with the problem of rationality, then you are able to account for bias? So is the focus more around accounting for rationality and somehow hoping that the efforts of bias in models that can come in when building a model will be dealt with and taken away?
Look, I mean, basically one of the reasons why human beings are considered irrational is because of biases, because they are fundamentally biased, So I have a little bit different view on machine bias. I actually think machines are more likely going to overcome bias than human beings. Because we tend to think of machines that are created by human beings. And maybe this term that was quite popular when I was doing my PhD 20 years ago, of evolving artificial intelligence, the artificial intelligence that actually evolves on its own, and the more it evolves, the more it sheds the biases introduced by human beings. I think if we just revisit that concept and start paying attention on evolving, not online learning, because people confuse evolution of machines with reinforcement learning. When it evolves, it means the structure of your machine is actually evolving, which means as the feedback from your reinforcement comes back, you don't just look at tweaking the weight, but you also look at tweaking the architecture. And with computational power, you can even now change activation functions so that because of what is the feedback that is coming, when you look at a machine and its activation functions, after so many iterations, it does not have those activation functions that were chosen by its human owner. And once we start doing that, then we will have a hope of controlling bias, which will be naturally much, much easier than controlling bias in human beings. Thank you very much. Just to end by a little story, when I came back to South Africa, I attended a dinner party, 2001. Mark Shuttleworth, I think, had just come back from space, and the president of South Africa did something quite special for him, which was a dinner, and I was privileged to attend it. So I met two people. One is a leader, a prominent leader of the EFF. I'm not going to name him because I don't want people to come to my office tomorrow. And he says, so what did you do your PhD on at Cambridge? I said, no, in artificial intelligence. He said, what the hell is that? Those are the words that he said, not appropriate words, but that's exactly what he used. Then I met Minister Derek Hanekom. I'm going to name him because he actually likes this story. He says, so what did you do your PhD on? I said, artificial intelligence. He sort of paused for a minute and he said, but why didn't you do it on real intelligence? Thank you very much.